So then we're going to get started here with obviously our first chapter, which is actually chemical kinetics. And like I said before, this chapter does have equations in it for sure and formulas. And then, we're kind of go away from formulas and stuff. Um, and this is a little chapter kind of leading us into equilibrium, which is the main sort of topic for the course. So let's talk a little bit about kinetics. So kinetics really deals with sort of the rates of reactions, how fast or slow a reaction takes place. Later on in the semester or chapter, I suppose, and it's just semester, well, we will talk about thermochemistry or thermodynamics. And thermodynamics, which you've talked about part of it probably in Chem 50, which was all that delta H, the energy, and all that kind of stuff. We will talk about the rest of thermodynamics, and really that part of chemistry deals more with whether or not a reaction will occur. And that's when we talk about a reaction, for example, being spontaneous. And as we'll talk about when we get there, again, sometimes people have a misunderstanding about the word spontaneous in terms of reaction. Sometimes they think spontaneous means that it's going to occur super fast. And that's really not the case. So later on, and when we talk about sort of reactions being spontaneous, typically what that means is under those conditions that we're talking about, that reaction should actually take place. And that's pretty much what it means. It could take place really fast. It could take place really, really slow. It could take place anywhere in between. And what sort of helps us understand how fast or slow a reaction takes place is actually the kinetics, which we're going to talk about in this chapter here. So kinetics deals with how fast the reaction takes place. And one of the things that we typically look at when we're looking at reaction is reaction rates. Or a rate in general is really how something is changing over a period of time. And in terms of reactions, we oftentimes look at the change really in molarity over seconds, right? So a reminder, right? Molarity is our moles per liter. So we're really looking at how the concentration is changing over time. And that gives us our reaction rate. So for this particular reaction here of like A goes to B, we could write what is sometimes referred to as a rate expression. And a rate expression basically expresses just that, how a concentration of, say, a reactant or a product is changing with time. So we could say that the rate in this case is equal to minus the change in the concentration. So that's delta, which means change in the concentration. And again, when we see those brackets, that means concentration. And that's pretty much molarity is what we're talking about there. The change in concentration of A over the change in time. And we could also write one for the product here, which is the rate is equal to the change in concentration of B over the change in time. Now, when we have a reaction like this, which is basically a one-way reaction, it's a one-way street, we would expect, obviously, like the arrow is pointing here, that this reaction is going to head from our reactants, right, which are over here, to our products, which are over here on the right-hand side of the arrow. That would mean that over time, we would expect the amount of A to increase or decrease. It should decrease, right? Because the only way to make products is we got to use our reactants to make our products. So on the same token there, we should expect our products to start to increase with time. So the reason there's a negative here for this guy and really not for this guy is for this reason. We should have our reactants decreasing with time, so we're going to put a negative there. And that's because overall, when we talk about typically the average rate of a reaction, which are these numbers, they actually need to be positive numbers. So they should really kind of be positive numbers. So if you just think about this reaction here, if we just sort of made up some numbers here, and initially maybe we started with 4 and we had nothing of our products, say molarity, whatever this may be. And at the end of the reaction, who knows, maybe we had 2 of this and maybe we had 3 of that, whatever it may be. So if we were going to calculate, for example, the change in the concentration of A over this reaction, we would take the concentration of A at the end, right, final, minus the concentration of A initial, right? And if we do that in this particular case, that would actually be final is 2 for A, and initial is 4. So that's going to give us a -2 molar in terms of the change in concentration. That negative that you get from this part, along with the negative we put in front, will then turn your rate into a positive number. So that is why we have that negative there. We don't need it on the product side because when we do the change in the concentration of our products, our final in this case, in my example, was 3 molar minus 0 molar. That gives me a positive 3 molar. So we're good to go. We don't need that negative there. So the negative there is really because the change in the concentration of your reactants, because they should be decreasing with time, will give you a negative change. And again, that negative will again turn your rate into a positive, which should be a positive number. Question on that there. All right, so these again are what are sometimes referred to as rate expressions. And the nice thing about rate expressions are if you really know how sort of one thing is changing in a reaction, maybe you know how one reactant is changing over time, or maybe you know how a product's changing over time, you could actually use the rate expression to figure out how everybody in the reaction is sort of changing with time. And you could also use it to basically figure out the average rate for that particular reaction as well. And in kinetics, we like a lot of graphs and we like a lot of pictures. So again, here, just visually looking, our A are sort of our black circles here. And you can see really at time 0, that's pretty much all we got is our reactants, which you can see here in the graph. As time goes on, we start to see the disappearance of the black circles representing our reactants. And now we start to see the appearance of our red circles here that represent our products. And over time, we can obviously see here we're ending up with a lot more products being formed, again, because this reaction is heading in this direction. So we do see a decrease here of our reactants. At the same time, we start to see from 0 our increase here of our products that are basically going to occur as this reaction takes place. Now, how can you sort of follow the change in like a concentration of a reactant or even a product? So for example, if you have something that has a color associated with it in a reaction, like here, this is Br2 plus a little formic acid. And this Br2 is actually that kind of orangey color there, or reddish color. And when we start the reaction, as you can obviously see, we have a lot of reactants present as indicated by the color. These guys over here are pretty much colorless, which is sort of where we're going to end up over here. And you can see as the reaction goes on, as those reactants are being converted over time, we start to obviously use up some Br2 and we start to see the color start to decrease. We get an increase in a lot of products which are colorless, and we start to see the color get lighter and lighter until obviously the reaction is sort of over and there is no more color associated with it. That's also really beneficial if you wanted to sort of quantitatively figure out what's going on. You want to get some numbers of, how things are changing. We could use a spectrophotometer like a Spec 20, like some of those things that you maybe have used before. And how basically all these sort of processes work is you have a light source at a specific wavelength. It shoots it through your sample. And usually it will hit the detector and it will measure one of two things, either absorbance or percent transmittance. Now, the absorbance of a solution is related to color, which is why this is a really good technique for something like this. The darker the color, the more light's going to be absorbed by the solution, right? Less is going to kind of go through to the detector. If you have a colorless sort of solution, obviously all that light's going to go through. Nothing's going to get absorbed by the solution. So the relationship that we use a lot in this class actually is Beer's law relationship here. This is what is sometimes referred to as Beer's law. A is the absorbance. B is what is referred to as Beer's constant. And C is concentration. And sometimes that is also given like A is equal to E, B, C, where that kind of epsilon, really not really E, but the epsilon there and the B are the path length and the molar assortivity. constant, and usually a lot of times that's sort of combined there into Beer's constant. We here at this school use really this version of it most of the time. So what that allows you to do is you could actually, if you were going to do this experiment, you can mix all your reactants together, and you basically can take absorbance readings all through a period of time, right? So over time, we'll start to see the absorbance go, actually in this case, down, right? It should start pretty high as we have a nice orangey red color to start with. As time goes on, we will see the absorbance value get lower and lower as it gets more colorless, and obviously no color at all. How do we know sort of when we do this, what wavelength to set it to? That's really important. A lot of times what you'll do is you'll take the absorbance value over a range of wavelengths. The nice thing about what we use here, and a lot of times is they'll just do that for you. You don't have to manually do that. They'll just kind of take it over electronically themselves. And usually what you'll see is this sort of peak over here. And this is the maximum absorbance at that wavelength. And what you would want to do then is kind of go down and figure out, what is the wavelength where you have your maximum absorbance. The reason you would want to set it to that wavelength and say not over here at this wavelength is if I set it way over here, do I have a lot of absorbance values I could actually read before I'm off the scale? I don't. I only have about that much absorbance values, and then I'm going to be off the scale, right? Here, I could basically take absorbance readings all through here, and we're going to be good. So that's usually why you want to do that. By the way, the light that is absorbed by the sample is complementary, right, to the color we see. So if our solution is red, we would not set the wavelength to red. We just set it to actually the complementary color to red, it's wavelength, because even though the solution looks red to us, that's actually not the wavelength being absorbed. So we see the complementary color to it. So that's also why if you look at it, you're like, hey, that thing's red. How come I'm not setting the wavelength to the visible part of the spectrum, right, where red is in that 700 range? It's because it's actually, in the complementary color. Any questions on that there? Now, because of that, the change in the concentration of Br2 is proportional. That's what the little symbol there means, proportional to the change in absorbance values. So like I said before, and you'll actually do this in the first real experiment, not the fake one we're doing today and the next day, but when we get to the real experiment, you'll actually do this. You actually do it in this experiment too, I think. But you'll take basically absorbance readings over a period of time. Using Beer's law, you can then convert those absorbance readings into concentrations, and then you'll know over a period of time how the concentration is changing. So again, a very common technique in kinetics that is used. Would this technique be good if the reactants and the products were both colorless? It would not, because you would get no absorbance and nothing would happen for you. Everything would be a flat line, basically, right? So it would not be obviously a useful sort of technique if your solutions did not have color. So you need some type of color. You either need color on the reactant side or you need color on the product side. Like eventually it starts at colorless and then kind of goes to a color. And in that case, you would see the opposite. If you started with something that's colorless and goes to a color, as time goes on, you actually see the absorbance start to increase, right, until you get to the end of your reaction. Any questions on that? So here again is a graph of this, say, reaction. And what we see here is the concentration of Br2 is decreasing with time, like we would expect in this reaction, again, because Br2 is a reactant. When we talk about rates, there's really kind of two types of rates that we sometimes refer to and when we're talking about it. Most of the time, we're talking about the average rate, and the average rate is essentially the change in the concentration of whatever you're looking at, basically over the whole entire time, basically. So from final to initial, over the time that it took final to initial. There's also instantaneous rates, which is really just sort of for a window of time, if we will, a certain period of time along the way. So you could kind of think of it like when you're driving, if you're driving, say, from here to Arizona, maybe along the way, at some point, you're doing 60, 65, 70, 75, 80-ish, 85, maybe. Hopefully not too much more than 85, I'd imagine. Although it is like 75 once you cross the border, so that's not too high up over it, I suppose. So at different points along your sort of journey there, you're traveling obviously at different speeds. If you average out your whole trip from beginning to end, maybe you only drove at 72 miles an hour for the whole trip. But again, at different periods, you would be going faster, you'd be going slower. And that's how basically these reactants and products are changing as well. Over a specific period of time, they may be changing faster, and then they may slow down and average out over the period of time that will happen. To find the sort of instantaneous rate, you usually take the slope of the tangent of the line here. And that is, you kind of draw a straight line between a couple of points and see kind of get like an X value and a Y value. I said that backwards, but you understand what I'm saying there. An X and a Y value there. And you basically take the slope of that line off of there if you had to do that. We're probably not going to do too much of that in here. But if you wanted for that period of time, you could do that. And you can see for those instantaneous rates, we do have different values. So just for that kind of window of time, things are changing a little bit differently. They're not constantly changing. And then if we kind of take it from beginning to end and get our average rate, we will have, sort of the average rate for the overall reaction. Now, if we were to look at this, there is a couple of or a value that is sort of constant when we look at these type of things. So as we saw, the sort of instantaneous rate is not constant, as you can see here at different periods of time. Again, things are changing faster or slower, right? You could think about like, at the beginning, there's a lot available, so you're going to have a lot of change occurring. As you start using up reactants, right, it's going to take longer for them to find each other, right, to continue to react. So the rate at which they're going to react is going to start to decrease over time, just based on the availability, right, of everybody being there. At the beginning, you got plenty. At the end, you don't have so much there. So you could write something for, say, this reaction, which is sometimes referred to as the rate law, which we will talk about here. This is what is known as like a rate law. And a rate law has this guy here, which is actually lowercase k, and I'll draw it dramatically small there. And that is actually the rate constant. It is lowercase k because, as we will talk about pretty much for the rest of the semester, capital K is the equilibrium constant, which is something slightly different in a sense, although they are sort of related to each other. You can take the rate constant, and if we rearrange this and solve for the rate constant, which is the rate divided by BR2 in this case, by just taking this to the other side and dividing, we will get this value here, which is 3.5 times 10 to the minus 3. Those are reciprocal seconds. And you can see there that that value for this reaction is a constant value over the whole period of time. You could think of the rate constant as kind of telling you how fast or slow the reaction is taking place in a sense. So if you have a really large rate constant, you typically will have a fairly fast reaction. If you have a really small rate constant, then maybe the rate of the reaction will be smaller. If you just think about it, we're basically just in this simple example, we would be multiplying these two numbers. So if this number is really large, it should turn our rate into a larger number. And if this guy is small, it should turn our rate into a smaller number. So it kind of tells you how fast or slow sort of the reaction will take place. Now, what happens if we have something that doesn't have color? Well, for example, here in this particular case, in this reaction, even though there is color, and they did that, I think, so you could actually see what's in there. Without it would not have color, but they just kind of did that. In this case, we have a little hydrogen peroxide, and we're going to have it decompose into water and oxygen gas. So all these guys are basically colorless. So obviously, using spectrophotometry, like we talked about a second ago, would be sort of useless in this case because really we have nothing to measure. But what we are producing in this case is a gas. And when we think about gases, right, we think about everybody's favorite gas law, which is the ideal gas law, right? PV equals nRT. When we use PV equals nRT, as you know, hopefully units do need to be specific. Pressure needs to be in what units? Atmospheres. Yep. Volume needs to be liters, right? And should hopefully be moles. Temperature always needs to be Kelvin. Reminder, right? Celsius plus 273, right? Gets us Kelvin. And R is our gas constant, so that's our 0.08206 liters atmosphere Kelvin mole. Maybe you'll learn 0.0821. People like to use a rounded number these days. Same thing. And that is obviously a constant. So in this case, because we are producing O2, we could actually use something like the ideal gas law. For example, if you took the ideal gas law, which is PV equals nRT, and you solve for N divided by V, it would equal P over RT. And N is moles, right? And V is liters. So that's basically solving for moles over liters. That is the molarity, right? So you could actually use the ideal gas law. And what you would have to only measure basically is pressure. Temperature would probably be the same in that experiment because you're probably not changing temperature. R is a constant. So this is a very simple way that you could, in this situation, measure the change in pressure over time. And you could actually then use something like the ideal gas law here to convert that into how the concentration is changing over time. If I was doing this, would my pressure be high to begin with or low to begin with? Would my pressure be increasing or decreasing with time? What do you think? It would be increasing with time because our reactant here is not a gas, right? The only gas is on our product side. So we shouldn't have any pressure until we start producing enough gas, right, on our product side to really start registering some pressure and stuff like that. That's how we know this reaction is actually taking place. If we start to see the pressure go up, we definitely are making the gas that's on the product side, and this reaction is actually proceeding, right? So in this case, we would actually see the pressure go from like 0 probably upwards to wherever it may end up at the end of the reaction. So again, this is another way that you could do sort of a kinetic study if you don't have anything that is sort of has a color associated with it, but maybe you do have a gas that's produced. Or if you have a reaction where you're starting with a gas and maybe you don't end up with a gas or something like that, you could then would follow the pressure decreasing with time as well. And that gives us, as I said, basically all you have to do is measure that change in pressure and you'll do the change in time. And again, that would then relate in this case to how the concentration of O2 over time is changing. Now, the concentration of O2 over time would actually be a positive number, right? Because again, it should be increasing with time when it's all said and done, because it is a product in this case. So when we look at rates and rate expressions, we do need to take into account stoichiometry, which everybody loves, right? And a reminder, our stoichiometry comes from the balanced equation, the coefficients. So in this case, we could say 2 moles of A equals 1 mole of B. And again, that is from our balanced equation in this case. We do have to take that into account when we're doing something like the rate expression, because obviously the stoichiometry affects at how things react and how much products produce, for example. So for example, if we were to write the rate expression for this reaction, we would say that the rate is equal to negative because A is a reactant. So again, it should be decreasing with time. The change in the concentration of A over the change in time, but we actually will take 1 over the coefficient. And by taking 1 over the coefficient in this case, it will actually combo for you both the kinetics calculation and the stoichiometry calculation together. So kind of do it all in one move. You'll take care of the stoichiometry and you'll also do the kinetics part of it in one sort of step. When we get to our product side, this should be increasing with time. So once again, we have no negative here. The coefficient is actually 1, so we don't include it here, but technically it's 1 over 1, which will give you 1 in this case. And that's the change in concentration of B over the change in time. Generically speaking, for any reaction, you basically can take 1 over the coefficient, the change in concentration of the reactant or product over time. Again, you got to put the negatives in there for our reactants and positives there for our products. What this allows you to do is, as you can see there on the bottom, you could set them all equal to each other. And what that allows you to do, as I mentioned earlier, is as long as you know just one piece of information, maybe you know the average rate, you can basically figure out how A is changing with time, B, C, or D is changing with time. Maybe you just know this, how D is changing with time. You could use that in these relationships then to figure out how everybody else is changing with time. So as long as you know, again, just one piece of information about anybody in that reaction, you could use these to relate to each other. So let's just say, for example, like I just said there, that we knew something about D, but we were interested in A. You could write the whole thing, or you could just write the two expressions that are in play here. And we could write just separately that the rate is equal to -1 over A, change in concentration of A over the change in time. And we could write the rate is equal to 1 over D, change in concentration of D over the change in time. Now, again, if I knew this part of it, I would know this from the equation. That would allow me to actually calculate the average rate for the reaction, again, if I knew that. And why that's helpful, because this rate right here and that rate right there are the same rate. So now I know this guy, which would then allow me to solve for something like this. So that's why I said if you kind of know one piece of information, it will really open up pretty much everybody else there. So you could absolutely do it like this, which might be a good way to do it, which is 1 over the coefficient. And again, like I said, what that essentially does is does the combo of the stoichiometry and the kinetics calculation together. If you wanted to, you could just do a regular sort of stoichiometry relationship first, if you want, like a mole to mole relationship, and then do the kinetics calculations separately. But again, this sort of combines it all together. So hopefully less chance for maybe some error in that case. But you can definitely just do like the stoichiometry part first and then kind of do the kinetics part separate as well in terms of the calculation. We'll see an example of that, I think, a little bit later, and we'll kind of explain how you can do both ways. Any questions on that so far? Okay. So why don't you write the rate expression for this reaction? Okay, so let's take a look. So here the rate would equal, we'll start with our first reactant here. It is a reactant, so we do need the negative. And again, the change in the concentration of CH4 over the change in time. That would equal our next reactant. Here also would need a negative because it's decreasing with time. We do need to go 1 over the coefficient here. Obviously here the coefficient was 1, so we don't really need to put the 1 there. The change in the concentration of O2 over the change in time. Now we get to our product side. We do not need the negative because they should be increasing with time. This would give us the change in the concentration of CO2 over the change in time. Once again, here the coefficient is 1, so we don't need to put 1 over 1 or anything like that. And lastly here, again, our water should be increasing with time. Here we do have a number, so 1 over 2, change the concentration of water over the change in time. Any questions on that there? And again, like I said before, in this case, if you knew just one piece of information, you pretty much could figure out how everybody is changing. Once again, you could calculate this would be the average rate for the reaction, which is typically, again, a positive number. And you can figure out how each of these individually would be changing with time. And if you're doing something like O2, it would be that whole thing is what you typically would solve for, how it's changing per time. Same thing with like water or something like that. Any questions on that? Okay. Yeah, it is always going to be 1 over the coefficient. Yeah, because that takes into account the stoichiometry that's going on. So if you're going to do this, which I would recommend, that does it all together. So it's always 1 over the coefficient. Yeah. Other questions? All right, so why don't we try one with numbers here. For this reaction, the concentration of I minus changes from 1 to 0.868 molar in the first 10 seconds. Calculate the average rate for that 10 seconds and what is the concentration of H plus over time, how it's changing. So see what you come up with. Okay, so let's take a look. So in this particular case, we are given some information about I minus, and in this case, we have it changes from 1 molar. So initially we're at 1 molar. It goes to 0.868 molar. That would be like our final there. And our time is basically 10 seconds. So you could probably assume that the initial time there is 0 and the final time is 10. And in this case, we are looking for really the average rate and how the concentration of H plus over time is changing. So what I would start with is really the two rate expressions that are in play here, and that would be from here and here. So we could write for our I minus that the rate is equal to, it would be negative because it is a reactant. The coefficient there for I minus is 3, 1 over 3, the change in the concentration of I minus over the change in time. We also could write the rate expression there for our H plus, which also is a reactant. So we also need the negative there. It also has a coefficient of 2. So that's 1 over 2, change in concentration of H plus over the change in time. First off, any questions up to there? Since we have the information for I minus, we could just plug it in there basically, and we can actually calculate what the first thing it was actually asking, which is what is the average rate of this reaction. So if we do that, we'll take our rate is equal to minus 1 over 3. Remember here that the change in concentration is final minus initial, 0.868 molar minus 1.000 molar, divided by, again, if you want to do final minus initial, or you could just do 10 on the bottom, but really it is final 10 minus initial seconds. More importantly, why is the top one more important there? Top one is going to do what? When I subtract that, what type of number do I get? Do you get a negative? So this is why we don't want to just take the difference, right? So if we take the difference, we will end up with a positive number and we will end up with a negative rate, which we should not have. So again, it's important to make sure that you always do the final minus the initial here. And if we do that, that's 0.868 minus 1 divided by 10. And we also want to make sure we divide it by 3. And again, that takes care of the mole to mole relationship or the stoichiometry. That's going to get us here that the rate here, or the average rate for this reaction, is going to be 0.0044. The units on top and the units on the bottom do not cancel, molar seconds. Yeah. Now, that is the average rate, and how that helps us with the H plus is we are ultimately looking for the H plus for this, right? So we're ultimately looking for this, which means we now just solve for that. So that's going to be really helpful here. So that would mean in this case 0.0044 molar seconds is equal to negative 1 over 2, the change in the concentration of H plus over the change in temperature. Since that is what we're looking for, we need to do what with the 2? We need to multiply it to the other side. By the way, it's not just the 2. We also need to multiply the negative as well, right? So we got to get rid of that on that side, basically take it to that side. And that will get us here negative 0.0088 molar seconds is how the concentration of H plus over the change in time is changing, or how the concentration of H plus is changing with time. That is a negative number, right? And that does make sense because, good catch. That does make sense because it is a reactant, so it should be decreasing with time, right? And that's what that negative implies. So if you're solving for how, for example, a reactant is changing over time, you should probably get a negative number, and it's okay that it's negative because that indicates that it's changing with time. If you're solving for a product over a period of time, how it's changing, you should really get a positive number because it should be increasing with time. But when you solve for the average rate of the reaction or just the rate of the reaction, that should always be a positive number. So that should always be positive. Reactants can be negative in terms of how they're changing. By the way, this also tells us that H plus is changing the same rate as the average rate of reaction, or is it changing differently? It is changing at the same rate as everybody else overall. It is not, right? So average, everybody into account is changing at 0.0044 molars per second, right? This guy's actually changing twice as fast as the average rate, right? And that's because his coefficient is 2 and the stoichiometry is twice as much, right? So you're using twice as much as this guy over a period of time, taking into account him and everybody else in the reaction. On average, everybody is changing on an average of 0.0044 molarity per second, but this particular reactant is actually changing twice as fast. Yeah. Any questions on that? So you have some that are changing faster, you have some that are probably changing slower, and when they average out, they get to that average rate of the reaction. Yeah. Why did we use hydrogen peroxide? We I only used I minus and H plus because I was only given information about I minus, and it was asking me to solve for H plus. So you don't. So that's why I pulled out. That's why I said before. I say in most problems you'd probably only use two things in there. You could be asked technically how everybody's changing if you wanted, and you could absolutely, if you wanted to know how, for example, you say water or hydrogen peroxide, either one, it doesn't really matter. You could actually figure out how that's changed. So, for example, if we looked at, and it wasn't asked in this question, which is why we didn't. But if you wanted to do hydrogen peroxide, it would be obviously the change in the concentration of hydrogen peroxide over the change in time. We could answer that really quick because we already know that's the rate, right? So hydrogen peroxide would be changing at that same number, basically. It would be 0.00, and it should be negative, by the way, 0.0044 molar seconds. We would need to take the negative back over, and that would be how that guy is changing with time. We could also do the same thing for anybody in there, but in this case, we was just asking about those two things, or really that one thing, and we have information about the other. So I would recommend not throwing everybody into the pool there. Just take out the ones that you need and write them separately, and then kind of do them that way. Other questions? All right, so I want to try this one here. If we have 2.4 times 10 to the 2 grams of NOBr, the molar mass from the periodic table, I'll put a mole in there, is 109.91 grams per mole. It decomposes in a 2 times 2 to milliliter flask in 5 minutes. Find the average rate. Okay, so let's see how you're doing. So in this particular case, they gave us the grams here of NOBr, which is 2.4 times 10 to the 2 grams. We have a volume here, basically 200 milliliters. And we have a time of 5 minutes. And we're looking for basically BR2's production. So we could write basically our two rate expressions. Obviously, we have information about this guy. So the rate is equal to negative, because that's a reactant, 1 over the coefficient, the change in the concentration of NOBr over the change in time. We could also, while we're at it, right where we want to end up here, which is the rate is equal to, again, it's going to be positive because BR2 is a product, so it should be increasing with time. Coefficient is 1, which means we don't really need to put anything there, and that's going to be a BR2 over time. So we do have enough information to go into here. We do need to do a little bit of calculation. We have grams and volume there, so we can calculate the molarity ourselves here using the molar mass that was given to us. So we have 2.4 times 10 to the 2 grams using the molar mass from the periodic table. If it was not provided for you, we want to put grams on the bottom so that they cancel, basically dividing, right? And that's going to get us here 2.4 to the 2 divided by 109.91. Get us a 2.184 moles of NOBr. This is basically 200 milliliters that can be converted to liters by dividing by 1,000, which is 0.2 liters basically in this case. And now we can actually get the molarity here. So our molarity of our NOBr would be 2.184 divided by 0.2 liters. So popping that in there, divided by 0.2, and we'll call it 10.92 molar. That is basically this guy right there. I also have the time given to me. By the way, any questions on that there? I do have the time given to me. It's actually in minutes, but I really know from my end here that I do want the time in seconds. So I'm just going to convert the time into seconds at this point. So everything's just sort of in the right units. And I don't have to worry about doing the conversion later. So obviously, hopefully 5 minutes, right? A minute is, I hope, still 60 seconds. We'll go with 300 seconds in this case. Yeah. So we have now what we need here and what we need on top, so we could put it into that expression. And if we do that, that would get us here that the rate is equal to -1/2, -10.292 molar divided by 300 seconds. By the way, why did I make that negative? It is a reactant, so probably how we got that number, right, was kind of final minus initial, which should yield you a negative number. Once again, here, if you don't recognize that, and they didn't say that with flashing lights anywhere, right, you will end up now with a negative rate, which you should not have. So again, we do need to incorporate the negative here because the change of that reactant should be negative over a period of time. Any questions on that there? All right, so if we do all that good stuff there, that's that divided by 300, dividing it by 2 to take care of our stoichiometry will give us 0.018. Again, the units here would be molar seconds. This would be the average rate for the reaction, which we can now use to really solve for what we're looking for, which is what we have on top there. The rate is equal to the change in concentration of Br2 over the change in time. And since that equals the rate, that is the answer for Br2 as well. Because it's basically equal to the average rate. This one is positive, which it should be, right? Because again, Br2 is, in this case, a product, and it should be increasing with time. In this case, Br2 is actually changing the same as the average rate of the reaction, basically, yeah? Any questions on that there? So as I mentioned before, this is a good way of doing it because it does sort of do the stoichiometry and the kinetics together. As I mentioned before, if you would rather just take maybe a stoichiometry approach first and then put the kinetics in, you can. So to demonstrate how you would do that, say in this problem is, we could actually just do what we did originally, was get the moles of our NOBR. So if we take the moles of our NOBR, 2.184 moles of NOBR, and we just do a mole to mole relationship between these two, that would get us 2 moles of NOBR is 1 mole of Br2. And if we do that, we'll get 2.184 divided by 2. We'll get something like 1.092 moles of Br2. We then could turn that into molarity by dividing by our 0.2 liters. And if we divide that by our 0.2 liters, that will get us 5.46 molarity. We then could divide that by the time, right? And basically our time was still 300 seconds, right? And we take that and divide that by 300 seconds. We will then get 0.018 molar seconds, which is the same answer. So you can do basically it's like a stoichiometry problem first if you wanted to, and then sort of incorporate into it all the kinetics information and calculations, and it'll come out the same. Or you could do it with 1 over the coefficient, and that will work out just fine. Why is it 1 over the coefficient? It's because of this right here, right? There it is, right? 1 over the coefficient, yeah. It's basically the stoichiometry part. So again, that takes into account and kind of does it for you when you do that. Any questions on that there?